This is the second of our two-part series on types of reactions, so don't write a new heading, just keep going with where you left off. The third type of reaction is single displacement. It's also sometimes called single replacement, and we're going to call it the cheater. It's really called single displacement, or SD. First of all, the general form is AB plus C produces CB plus A, which means that we're assuming that both C is a metal, so metals I'm going to underline in green, so C obviously is a metal, and because it took the front spot, A obviously is also a metal. So in this situation, metals would always be in front. It's possible for the element C to be a non-metal, in which case it would have taken the place of B. The reactants have to be an element and an ionic compound, and that ionic compound usually is dissolved in water. For example, if we take sodium metal and add it to magnesium chloride in solution, we can get sodium chloride solution and magnesium metal coming out of it. The key feature is that the element has to replace a similar element in the compound, which means if I'm putting in the unique element sodium, which is a metal, it's going to remove the magnesium, it'll never remove the chlorine, so you're never going to get two metals or two nonmetals teaming up like that. The reactions are only going to actually occur if the element that's being added separately, that C from that general form, is more reactive than the metal that's in the compound. And that's a detail that we're going to go into more in detail in your grade 11 chemistry class when we talk about the activity series. So why do we call this the cheater? Well, here's that lovely couple that we had back in synthesis. Who's this? Oh, pretty girl with a red bow in her hair. She's stolen him away. Or maybe he just left. He must be the cheater. That left the girl in the yellow dress all by herself. Oh dear. Moving on in 3, 2, 1. Double displacement is also known as double replacement, and we're going to call this the swingers, but it's really double displacement. So the general form is AB plus CD makes AD plus CB. Notice that A and C are both metals, and B and D are both non-metals. The reactants must be two ionic compounds, and they're both going to be dissolved in water when this is working. For example, in your lab that you did over the weekend, we had sodium carbonate and calcium chloride reacting to make sodium chloride and calcium carbonate. One key feature of this is when they react, you're going to get either a solid, a gas, or water. And in this case, what we had was the calcium carbonate happened to make a solid, and the sodium chloride was aqueous. So here's that lovely couple from synthesis again with a lady in a red dress and a guy in a purple hat. So why do we call them double displacement? Well, looks like this guy's come in, taken that guy's spot. Oh, and he's gone and taken that spot. So they've simply swapped positions. And moving on in 3, 2, 1. The last reaction type is combustion, which most people simply refer to as burning. Combustion requires a very simple situation. The general form is some material plus oxygen gas makes some oxide material. And that depends entirely on what X is, because lots of different things can undergo combustion. You have to have as reactants oxygen gas and some kind of fuel. The fuel could be a metal, like magnesium, reacting with oxygen gas to make magnesium oxide. It could also be a nonmetal, like sulfur. These two reactions I'm actually going to demonstrate for you when we get into Chapter 7 dealing with acids and bases, because it fits better there as a demonstration. We can also burn, hey wow, I've got example 1, 1, and 1. Let me fix that to be 1, 2, and 3. That works better. So if we take a hydrocarbon, which is simply a chemical that contains a mixture of carbon and hydrogen, like CH4, that's methane or natural gas, and you burn it in oxygen, you'll always get water vapor. If there's not enough oxygen gas to convert all the hydrogens to water, the reaction just won't happen. However, it depends a lot on how much oxygen you have present for this type of fuel. If you're going to get complete combustion, that requires lots of oxygen present. It's going to be really hot, and you're going to get carbon dioxide gas. And that is that nice blue flame. So when we're using a Bunsen burner, that's the one we typically light. In contrast, incomplete combustion means that there's less oxygen, so we don't get as much combustion going on. The flame is cooler, and that cooler flame is the yellow flame. And that's the one we don't like partly because it's cooler, so it doesn't get as hot, but also because it releases some combination of carbon monoxide, that's CO gas, and it's deadly in small amounts. It connects to your red blood cells and makes them unable to carry oxygen gas, and so you very quickly suffocate. If there's even less oxygen than that, you'll make carbon soot, and many of you saw that when we were burning our filter papers, we had that black soot forming on the bottom of our crucibles, and that's because the yellow flame didn't get enough oxygen, and as a result, we got that soot forming on the outside. So that's our 5 types of reactions: synthesis and decomposition from the first movie, single and double displacement from this movie, and combustion. In class, we're going to be doing 2 different labs. The first one is section 6.8 from your textbook. We're going to be merging those into one lab that we can do in a spot tray fairly easily. And then the other lab, we're going to have a series of stations where we're going to be burning 2 different fuels for each group, just so you can contrast their behaviors. Thanks for watching.